Hello friends. So, we have seen how to solve the initial value problems first by transforming into first order differential equation by suitable addition of auxiliary equations and first order derivatives. I mean first order equations can be solved using several techniques, and we discussed Euler forward Euler, backward Euler, and then Rangakatta and then Adams family of methods. And they are in general, I mean Rangakatta particularly fourth order method is very accurate and very efficient technique, and is the go to algorithm in case of very severe nonlinearities and chaotic system analysis. But for normal vibration analysis with not very strong nonlinearities, then second order differential equation can be solved directly, and generally second order accuracy is still available, and that is good enough for engineering purposes, and particularly the advantage being we need to solve almost the problem size becomes half, because if we need to convert a second order differential equation into an equivalent first order differential equation, the size of the problem increases by a factor of 2. So, that way it is advantageous to solve directly the second order differential equation. So, we discussed several of the schemes starting from Hubolt method and central difference method, and then Newmark beta, and then recent additions of HHT alpha, Hilbert-Hughes and Taylor alpha method, and then Bossach's modification based on successive over relaxation on Newmark's algorithm. So, now during the discussion of the development of those methods, we had mentioned that some of the parameters are determined based on the stability constraint. We did talk about unconditional stability of constant average acceleration method and conditional stability of central difference method. So, what do we mean by this concept of stability of numerical scheme or time marching scheme, and how do we assess them, and what is the impact, or what does it convey the notion of stability of time marching scheme. So, we in this lecture we will discuss about the analysis of this time marching schemes. How do we judge the quality of these algorithms or the parameters of the algorithm, and if we are required to choose suitable parameters of the algorithm of a given algorithm, for example beta gamma of Newmark algorithm, then how do we choose beta gamma other than linear acceleration and constant average acceleration choices. So, whether any other variation and leading to different values of beta and gamma, whether they would be admissible for acceptable accuracy, do they guarantee admissible or reasonable accuracy for computation, and usability of research results. So, that is what we discuss in this lecture today, analysis of time marching schemes. And as I have been emphasizing again and again, all numerical computations are at best approximations. So, it is a myth to talk about exact solution for anything coming out of digital computer. Digital computers cannot provide us exact solution. All solutions, all numbers returned by the computer, they are approximate numbers. So, time marching schemes, they involve a lot of floating point multiplications in approximate solution of differential equations. So, if you recall, the entire development of floating time marching scheme is solution of linear simultaneous equation at every instant of time. The second order schemes that we developed, I mean whether it be Hubolt method, Hubolt scheme, or central difference scheme or Newmark beta scheme, HHT alpha method. So, all of them they essentially involve solution of simultaneous equations at each instant of time, and then knowing the values at each instant or at a given instant of time, all displacements, velocities and acceleration at an instant of time, then we use this for advancing the solution in the next to the next time step. So, these repeated floating point operations, every, as I keep on saying, every floating point operation is a source of error. There are round of errors that are incurred in every floating point operation. In addition to, of course, multiplication is the most expensive operation. I mean, second only to division. Division is even more expensive than multiplication, slightly more expensive. So, the natural question comes, if I compute the solution at nth time instant, there are lots of floating point operations happening at nth time instant, and the solution that we compute at nth time instant, that is an approximate solution full of round of errors at every stage. And I use this information to compute the solution at the next time instant, n plus 1th time instant. So, I am essentially piling up errors, round of errors on top of round of errors incurred in all previous time instants. And that is a if you think about it, then it is a cause of alarm. I mean, till the end, I am keeping up adding error on top of earlier errors. So, how long can this go, and how long before the results become useless, if they are to become useless, that is. So, that is what the errors at one step of computation tend to propagate and affect the computed solution at all subsequent steps. So, the pollution, I mean the errors incurred at one step, it will tend to pollute the solution computed at all other subsequent steps. So, how to ensure that the computed numerical solution is representative of the true solution? It is a representative of the true solution. We can never hope to get the arrive at the true solution, but what we can do, and we can achieve that, it is very much within the domain, I mean our capacity of numerical techniques, to arrange our computations such that the computed result gives a reasonable representation of the true solution. And for this purpose, it is important to identify, we need to know thy enemy, that is the first rule of any combat. So, we need to identify and control the potential sources of errors in computations, in these computations. So, just as we identified the sources of error, the main source of error propagation in Gaussian elimination, that is of small pivot, and we found a workaround that we can use a pivoting strategy and interchange the, reshuffle the order of equations for elimination of variables, and that actually eliminates the problem of error propagation in Gaussian elimination. And we do the similar kind of exercise, we try to find a systematic way of tracking down, to analyze, to identify if there is any potential error, potential sources of error or potential problems with the parameters of time marching scheme that we are using. So, three terms are important in this context, and this is a very useful theorem. We will see why it is so useful and so often referred to. Lax Ritmeyer equivalence theorem, and it says for consistent numerical approximation, stability, the concept of stability and the concept of convergence, they are equivalent. So, the idea is if the approximation is consistent, we will come to the definition of consistency in a little while. So, if the numerical approximations are consistent, then if we can prove stability, then the convergence is implied, or if we can prove convergence, then stability of computation is implied. We need not prove stability and convergence both. This convergence is associated with accuracy. I mean, we converge to the true solution or accurate solution which is representative of the true solution. And consistency implies that, I mean, it is a discretely sampled data. So, we are not looking, we are looking at discrete time steps. Delta t is the interval of time step, then all we are looking at is solution at discrete intervals. So, we evaluate the motion, I mean equation of motion is we know the initial conditions at t is equal to 0. Next, from starting from t is equal to 0, we evaluate the solution at t is equal to delta t. Whatever happens between 0 and delta t, we do not know, we only impose the equilibrium at delta t, and knowing the solution, computing the solution at delta t, we then predict the solution, estimate the solution at 2 delta t. So, the point is we are looking at discretely sampled data, and consistency implies that this discretely sampled data is actually the continuously sampled data. It will reduce to continuously sampled data, or it tends to continuously sampled data in the limit as delta t becomes 0. So, as delta t, I mean if we reduce the time step smaller and smaller, I mean to smaller and smaller, so it becomes a continuum. So, that is what consistency implies. So, all these discretely sampled data, they are essentially samples of the values of the continuous waveform. As delta t tends to 0, it will converge to the continuous waveform. So, f n times delta t approaches f of t as the continuous variable time, and displacement u of at n times delta t converges to u of t as delta t approaches 0 as an approximation for difference equations in u t via finite differences. So, all these second order schemes that we had discussed, they all are derived, or they can be derived by using finite difference approximations of derivatives. So, this is consistency, that finite differences that we have and the discretely sampled values, they would represent, they would approach the continuously sampled waveform as the interval or the difference interval of time delta t approaches 0. So, if the approximation, this is of course the approximation, nature of approximation. So, if this nature of approximation is consistent, so numerical approximation that we are making, if this consistency property is adhered to, then we need to look at stability, and stability implies, I mean the notion of stability is very we all understand intuitively what is stability. It only means that if to any system, if the input is bounded, the response of the system is going to be bounded. It is impossible for any system to have infinite or unbounded response for a finite input if the system is stable. If the system is of course unstable, then even for small nudge it can actually build up response to very large level. And just as we mentioned, for a consistent approximation, stability of computation implies convergence. So, if the approximation is consistent and we can prove that the computations are arranged in a stable manner, then convergence is ensured, and that is the importance of this theorem, Lax-Rittmeyer theorem. Because we will see stability of a computational algorithm is often easier to prove than convergence, because in order to prove convergence we need to know what is true solution, and in most of the times we do not know what the true solution is. Had we known true solution, then there was no need for any computation subsequently. So, convergence is very difficult to achieve. At best we can look at convergence in Cauchy sense for finite element solution by different mesh sizes, and we can look at the convergence of those results. But in the case of time domain, that is not really a very convenient proposition, because that would involve repeating the calculations for different time steps. So, I do it for delta t, I do the same analysis for delta t by 2, I do the same analysis for delta t by 4, and then see if the results are converging. And most of the time the excitation itself is not defined at such fine intervals. So, delta t by 2, delta t by 4, the excitation may be available only at maybe samples of delta t interval. So, what do I do between delta t by 2 and delta t by 4? So, by approximating we can of course use linear interpolation to generate data, but that is another approximation that we are introducing, another source of error that we are introducing, because linear interpolation does not really satisfy the does not agree with the rules of discretely sampled data in the frequency content. So, that is it violates the Nyquist frequency criteria. It will generate frequencies beyond that, and it can lead to other issues, but let us not get into that. Suffice it to say that it is much easier and much more convenient to analyze the stability of algorithm, and if the approximation is consistent and we can prove the stability of algorithm for whatever operating parameters of the scheme, time marching scheme, then the convergence of the computed solution or the time marching scheme is guaranteed, and that is the reason for taking up this analysis of time marching scheme, so that we can be sure under what conditions the results of time marching of any particular time marching scheme can be relied upon. So, while stability of a computational algorithm is easily examined, it is much more difficult to establish convergence because of the reasons I mentioned. Convergence would require study for different step sizes, and that is much difficult job than studying the stability of a computational algorithm. Stability of a computational algorithm can be done on the analytical using certain analytical principles, and no further computation is generally required for that purpose. So, eventually all time marching schemes, whether it is first order techniques or second order techniques, eventually all time marching schemes can be arranged in the form that the solution at n plus 1th time instant, they are given as, they can be represented as some amplification, some effect of the solution at the previous time instant. So, nth time instant, displacement and velocity, and some effect of the forces or external loads at the current time instant and the previous time instant. So, the at n plus 1th time instant. So, the force at nth time instant and n plus 1 time instant. So, matrix A here, that is referred to as amplification matrix, because it amplifies the effect of initial condition, so to say, because in the beginning at time t is equal to 0, these will be the initial conditions, and these will propagate through the subsequent analysis in gradually. And B, which gives the contribution, controls the contribution of these external forces at 2 time instants, nth time instant and n plus 1th time instant. This is known as the load matrix. Now, let us assume lambda and phi, they represent the eigenvalues and eigenvectors of the amplification matrix A, right. So, we look at this amplification matrix A, and it is a matrix, square matrix. So, it relates 2 by 2 to 2 by 1 vector to another 2 by 1 vector. For this is for single degree freedom system, otherwise it will be 2 n by 1 relating to 2 n by 1. So, it becomes 2 n by 2 n matrix, where n is the number of degrees of freedom of the system being analyzed. So, if lambda and phi, they represent the eigenvalues and eigenvectors of the amplification matrix, then by definition of eigenvalue problem, standard eigenvalue problem, A phi is equal to phi lambda. Lambda is of course the diagonal matrix of eigenvalues. And by virtue of orthogonality of eigenvectors, the initial condition, vector of initial conditions u 0 and u dot 0, it is a vector in the same vector space, and that can be represented as a linear combination of the eigenvectors of matrix A. So, I can represent u 0 and u dot 0 as a linear combination of eigenvectors. So, C 1 phi 1 plus C 2 phi 2 plus C 3 phi 3 and so on, as many terms as the dimension of the system. So far so good. So, this is based on the orthogonality property, and that allows us to use eigenvectors as the basis of expansion. We can expand this vector of initial values into a linear combination of the eigenvectors. So, let us consider the homogeneous solution due to non-zero initial conditions. So, let us for the time being, let us forget about the loading condition. So, how the system, how the analysis techniques, the time marching schemes, they would predict the free vibration solution, that is how the system will oscillate or vibrate if it is disturbed from its initial position by for some non-zero initial conditions. So, the non-zero initial conditions, they are given as u 0 and u dot 0, and if we multiply, I mean V 1 as a if one step amplification. So, at first time step, it will be A times initial conditions at time t is equal to 0. So, that would be A times V 0. So, V 0 is the state vector. So, u 0 and u dot 0 comprising of u 0 and u dot 0. So, we have A times and we already defined V 0 or u 0 u dot 0 as a linear combination of eigenvectors of matrix A, amplification matrix. So, we can replace u 0 and u dot 0, vector of u 0 u dot 0 as phi c. So, this phi c represents u 0 u dot 0, and phi being the eigenvectors, matrix of eigenvectors of matrix A, this is A phi is equal to phi lambda by definition of eigenvalue problem. And the next step, having computed this V1 or the solution at free vibration solution at one step beyond the initial condition, then we go to the second step. So, solution at twice delta t. So, V2 is equal to A times V1 previously computed, just previous time instant solution. So, again we have substituting for V1 from here, we get A times phi lambda c, and again A phi is equal to phi lambda, and lambda is a diagonal matrix. So, it simply becomes lambda square and so on. So, at nth time instant we will have this solution as A times phi lambda raised to the power n minus 1 c, and that will again A phi can be transformed to phi lambda. So, eventually we will have phi times lambda raised to the power n c. So, the only thing that is changing, I mean if you look at this trend, the only thing that is changing here is the power of the eigenvalue of matrix A in each time step. So, for the first time step it is first power of lambda, second time step it is second power of lambda, and for nth time step it is nth power of eigenvalues. Eigenvectors remain the same, the coefficient vector c remains the same. So, the solution at different instants of time for free vibration, that is only given by the powers of the eigenvalues of amplification matrix A. Now, what does this mean? So, solution at successive steps differ only in the exponent of eigenvalues of the amplification matrix. Now, what are the implications for choices of eigenvalues? Nature of eigenvalues of amplification matrix controls the solution characteristics, obviously, because that is the only thing that is changing. Phi is constant and c is constant. So, if anything has to happen to the solution, it has to happen because of these eigenvalues. So, nature of eigenvalue depends on or governs the solution characteristics. So, what are the nature, what will happen if the nature is let us look at the possibilities. So, if the solution there are several at least there are three possibilities. If all eigenvalues are real and positive, right. So, if all lambda, if they are real and positive, then there is absolutely no scope of any change in sign in a different time step. So, whatever is the sign of this solution at first time step, that same sign will continue all over, or whatever is the sign of the solution, whatever is the nature of solution at the initial time step, the same nature will continue all through, right. It is not going to change sign at all. So, that implication is there is no oscillation. If lambda is real and positive, then it is all being multiplied again and again, again and again, again and again. So, it is a positive number. So, it is never changing sign. So, that is something that is very odd. I mean, how do I have a vibration solution without ever changing sign at any time instant? So, and this is guaranteed. If lambda is positive, real and positive, then there is no scope of any sign change at any time step. Time step you can keep on computing at any large number of time steps, and this will never change sign. So, obviously, that is a problem, and oscillatory motion cannot be captured. So, even if the problem is that of a vibrating system, mechanical system undergoing free vibrations, if the algorithm is such that the amplification matrix A has eigenvalues which are all real and positive, all eigenvalues of the amplification matrix are real and positive, then it cannot capture the oscillatory motion, and obviously that is a problem. And any such algorithm, any such choice of parameters which renders eigenvalues of the amplification matrix to be positive and real, they are all eigenvalues. Some of them can be positive and real, no harm, but all eigenvalues, the emphasis is on all eigenvalues. So, if all eigenvalues are real and positive, then we are looking at a problem. Now, look at the other part. If all eigenvalues are real and negative, so we first case we dismissed it off as not admissible, all eigenvalues real and positive. Now, the other alternative is all eigenvalues are real and negative. In that case, because the powers are, I mean, first is it is odd power, then it becomes even power, then it will be odd power, then it becomes even power. So, if these eigenvalues, all eigenvalues are negative, then there is going to be a sign change, forced sign change at every time instant, and that time instant is not related to I mean, these are only referred to as 1, 2, and delta t might be changed, might be different. So, different choices of delta t might actually give us different results for a given time instant. So, very untenable situation. So, if all eigenvalues are real and negative, there will be sign reversals at every time step, irrespective of the step size delta t. So, whatever may be the delta t, so there is going to be sign change at every time step, and that is a problem. If I use this, let us say for the choice of delta t, I have amplification matrix which has all eigenvalues as real and negative. Then let us say initial conditions are positive, then the solution predicted at delta t is going to be of opposite sign. So, it will be negative. Now, if I use the same amplification matrix, but I try to compute it at delta t of is equal to, now the I use the half of delta t. So, now the next computation is one is at 0 and another one is at delta t by 2. Now, the negative sign is for delta t by 2 and at delta t it becomes positive again. Now, that is a problem, just because of by the order of the, I mean, the size, now by changing the time step, size of the time step, the solution should not be so sensitive to that, and now it is impossible to reconcile which one is the correct solution. One solution gives me negative values, another solution gives me positive values, and if I choose any other delta t, I might get something else. So, it is a complete chaos there. So, obviously, this is also not tenable. All eigenvalues cannot be real and negative. Now, let us come to another interesting possibility. If the eigenvalue is complex, let us say at least one eigenvalue is complex, forget about other eigenvalues, at least one eigenvalue, let us look at one eigenvalue. So, what happens to that complex eigenvalue, nth power of complex eigenvalue? So, nth power of complex eigenvalue, I can represent lambda, if lambda is a complex number, I can represent it in this form, polar format, in the modulus and phase form. So, nth power will increase the amplitude by nth power, and it will also introduce a phase shift by n times, right. So, everything gets so exponential, it gets added up for every multiplication. So, it will be n times for n times amplification, there will be a phase shift of n times, and this is complex exponential. So, complex exponentials are essentially sinusoids, sine waves and cosine waves, and now we have a hint of oscillatory motion. So, there is a possibility of oscillatory motion can exist, and another thing is the amplitude is this. So, amplitude can either, if lambda amplitude of this eigenvalue, if it is equal to 1, then no matter how many times I try to amplify it, its amplitude does not change. And if its amplitude is greater than 1, even if it is slightly greater than 1, 1.1 or 1.01, then this term lambda I raised to absolute value of lambda I or modulus of lambda I raised to the power n will keep on increasing as the time step increases. So, essentially the solution will start and it will begin to diverge gradually. So, that is an unstable phenomena. On the other hand, if lambda amplitude of lambda is less than 1, then the solution will begin to decay, and this decay by virtue of this lambda is what we call as algorithmic decay, algorithmic damping. This simulates the damping effect, and that is coming entirely purely because of the parameters of the time marching scheme. So, these possibilities, hence the parameters of time marching schemes should be selected so as to admit at least one pair of complex conjugate eigenvalues of the amplification matrix. So, all the parameters for example, Newmark's scheme beta gamma and using HHT alpha, the alpha parameter which is again controlling beta and gamma, and again the Bosak's amplification, Bosak's modification algorithm. So, they all these parameters can be the bounds that we arrive at. For example, alpha was found, the bounds of for alpha are found to be between -1/3 to 0, and it is said that if alpha in HHT alpha method, if alpha is in this bound, then the algorithm is stable. And when we say stable, it essentially means this, that lambda, value of lambda is going to be less than 1. If beyond this, it may exceed 1, and even if the oscillatory motion is there, the amplitudes may keep on increasing even if there is no reason, physical reason to justify that amplification of amplitudes. So, in order to keep the solution bounded at all times, it is essential that the magnitude of none of the eigenvalues should exceed unity, and that means spectral radius of the amplification matrix should be less than or equal to 1. So, spectral radius, that is the largest eigenvalue of the matrix amplification matrix A, should be less than or equal to 1. If it is less than 1, then it is going to experience decay at every time step, and that decay is purely because of numerical nature, because of the parameters of the time marching scheme, and if it is equal to 1, then there is not going to be any kind of algorithmic decay, as what happens in the case of Newmark's constant average acceleration method. So, Newmark's constant average acceleration method, there is no algorithmic decay, algorithmic damping. And finally, we also look at what is the time step that is required for spatial discretization, because that is a information propagation. So, how the information propagates in space, I mean waveform, I mean waveform has to propagate through the medium. So, how do I define what is the what time step is required for a given choice of spatial discretization, finite element discretization. So, that is defined by CFL, what we call as CFL criteria, Courant, Fredericks and Levy criteria, and that is governed by a physical domain of dependence must be contained in the numerical domain of dependence, and that is called CFL condition, and this is a necessary condition for stability, but not a sufficient condition, and this criteria is defined as C times delta t divided by delta x should be less than 1, where C represents the largest velocity in the system at which the information can propagate. So, whatever is the that depends on the properties of the medium that is being modeled, and delta x is the spacing interval representative mesh size, and delta t is the time step that should be taken. So, it is this choice of time step that is important. What should be the time step that should be used for analysis purposes, but most of the time in practical problems we rarely need to look at this, because the excitation is often sampled at time step that is way below the limit imposed by CFL criteria. So, information of the distribution of primary variables ut in one time step should not advance further than the adjacent node in the spatial discretization. So, that is what this represents, this means physical domain of dependence must be contained within the numerical domain of dependence. So, one time step should not go beyond, information should not propagate beyond one adjacent node in the spatial discretization. So, again referring to algorithmic damping and period elongation. So, these are some of the performance of different schemes. So, RK4, that is this solid line, this represents the Runge-Kutta fourth order method. Then Newmark constant average acceleration. So, this is constant line that you see dotted line. Newmark linear acceleration. So, this is it is this particular line, and Wilson theta is this cross dotted and with cross. So, as you can see, the spectral radius, it remains reasonably close to 1 for some choice of ratio of delta t versus delta natural period T n, the natural period of the or the time period. So, and that gives us an idea from this spectral radius context that we should choose delta t. I mean delta t will affect the parameters of amplification matrix, choice of delta t. So, choice of delta t should be often I mean if we look at these curves, then it suggests that 10% of the natural period of the system is a reasonably good choice for delta t. The parameter spectral radius is close to 1, although for some of the algorithms it is slightly less than 1, but that is little bit of algorithmic damping is always better than running into instabilities. And this delta natural period that we are looking at, that should correspond to the shortest natural period or the highest frequency that we want to represent in the solution. Not all natural period, not all modes are required in the computation, or they are reliable, and therefore, this choice of T n or the natural period depends on what is the highest mode, that normal mode that needs to be represented in solution. And this is the phase change as we because if we look at the term involving complex eigenvalue. So, at each instant of time there is a phase shift, and this phase shift will push the solution ahead, and that makes it again phase distortion, that actually makes it solution to move slightly away from what is the true solution, and this is what we call as phase distortion. And every time step it will introduce an additional phase shift than what is actually there. And this phase distortion is generally very small, as for delta t for small time step, but it increases considerably as delta t increases beyond 10% of natural period. So, again it is a fortuitous I would say that phase distortion is under control for the choice of time step, that is about 10% of the natural period of the highest mode. For all lower periods, this is of course going to be much smaller. And this is what we mean by algorithmic damping and period elongation. Period elongation is, this is the true solution, and computed solution might look like this, and this is period elongation that we represent here P e, that is entirely because of this phase shift that happens at every time step that we compute the solution. And this decay in amplification amplitudes, this is entirely because that is called algorithmic damping, and this is because the magnitude of the spectral radius of amplification matrix is less than 1, and the even if the solution true solution does not have any damping, the numerically computed value might indicate some damping. So, cumulative effect of amplitude and phase changes over a time period would show up as period elongation and algorithmic damping. So, these are the two these are the techniques, these are the basic issues that we look at for during the analysis of time marching schemes. So, it is essentially the amplification matrix corresponding which affects which governs the how the initial conditions would be propagated over a period of time for free vibration analysis, and a simple technique that we use for testing the any time marching scheme parameters is to try to compute the free vibration solution for two sets of initial condition, one for unit displacement and 0 velocity. So, the computed solution should actually give us perfect sine wave, that would be cosine wave essentially, and the other one is initial displacement being 0, but the velocities are unity. Then the computed solution would correspond to a sine wave. And if the algorithm time marching scheme correctly propagates these pure cosine wave and pure sine wave for these two initial conditions, then there is that is a reason enough to believe that the computed response for any transient analysis, vibration analysis would be reasonably accurate. So, with that we complete our discussion of time marching schemes, and next lecture we start with a very exciting topic, although I get to spend very small amount of time in comparison to the significance of that topic, but I hope I can generate enough excitement for you to follow it up on your own, the Fourier transform and the fast Fourier transform algorithm and the analysis in frequency domain. Thank you.